Hi, hello. Welcome to the Exam 2 review. QR code for today. The question is, what is the question? I just had it the other day. Let me know once you scan. You biked past me on Mass Ave the other day. Yeah.
You also biked past me.
Out here zooming. What's the question on the thing?
What's the best thing on TV?
Yeah. I'm not watching TV right now because I'm doing some organic chemistry, which is probably the case for many of you. But what's the best thing? What should I watch once I'm free? Once you're free, what should you watch? Okay, so our game plan for today is we're going to do a little bopping back and forth of some practice and review of kind of the major reaction types and concepts and kind of commonly missed mistakes. And so it's going to be pretty like bip bop. We're going to go talk a little and do a little practice, talk a little bit, do a little practice, and so on and so forth. I did make this practice with the exam in mind and kind of like what like final stumbling blocks are or what kind of common challenges in the past have been. This one also has some of my favorite orgo memes. Is your child texting about organic chemistry? Boy, that's Vidig. Oxidizing my Grenier. Oh my gosh. BRB, beware regioselectivity, bro. That's about Markovnikov's rule. Yeah. But anyway, so we'll start off by doing analysis of the practice exams and talk through and kind of an outline of what the exam's going to look like. Any logistical questions before we jump into that? Cool. I'm not going to talk through the outline. It's just there for reference. Analysis of the practice exams. So a year or two ago, I spent like 3 or 4 hours, and I just kind of went through each question on the practice exams for the most recent ones, A and B. And you can see that they have the same framework, but I tried to kind of like diagnose like what's the core part of this question for all of them. And this is kind of a box of all the upshots. So 9 pages. You're going to have 3 pages of box problems. The first page of the exam is definitely going to be substitution elimination. Just like the practice exams, it's going to be the exact same format. And then the other 2 pages are going to be mixed of all the reactions. One of the pages will be completely just predict products. So you will give starting materials and reagents and arrows, and then you have to like put the product in the box. And then the other page is going to be half getting the reagents and the arrows and half doing the starting materials. So you're going to have some of the backwards thinking questions as well. Then you're going to have after that, and if I go in order, the next 2 pages are like theory and reactivity. So these are, you're definitely going to have aromaticity. You're definitely going to have stuff about directing effects and activation and deactivation of benzene rings, all kind of lecture 9 stuff. Outside of lecture 9, you might have to rank carbocation stability, or you might have to rank speed for SN1 or SN2 reactions. You could have to do like a little small mechanism that has to do either with like a rearrangement or stereochemistry or something. Yeah, that's kind of generally what the theory reactivity pages look like. I think on some of them there's even been like an acid-base question to kind of bring some of that back. And then after the theory reactivity, we'll move into the mechanisms. These are the kind of mechanisms that were laid out for like what they've been kind of in the past several years. And so like Wittig, alkene additions, radicals, nitrile hydrolysis, Sokol, EAS reactions, amine-enamine formation, or hydrolysis. Those are all kind of like classic examples of like, if I'm like, oh, I need to finish writing a test, let me just pull the mechanism. It would probably be one of these. These are the big ones. I will go ahead and confirm that the radical mechanism is on tomorrow's exam. So you will have a radical mechanism tomorrow that's only radicals, and then you will not have radicals on the final. And then I'll also confirm that we told you when the synthesis is going to be a DCC synthesis. That one's going to be tomorrow as well. So you're going to have a DCC synthesis on the exam tomorrow, but not on the final. Now, ways that we can make mechanisms harder. We can do a reaction that you've already seen with a little like twist. remember when we're in kind of a carbocation space, carbocations can do funky things and do little rearrangements. So that's often a place where we see kind of weirder mechanisms. And I think the practice exams give you a good idea of the like mechanism with a little twist of like, I think there was one that was like a BR2, but then there's like an OH next door and it does like an intramolecular attack. But for those, like we give you the products as well, so you're going to be able to kind of reverse engineer a little bit of it. Yes, and then synthesis are the final 2 pages. One of them is going to be like amino acid DCC synthesis. The other one, some ideas that we've seen. So we know VIDIG is like a really powerful way of joining together 2 molecules. Ozonolysis is a really powerful way of splitting apart 2 molecules. You might have to do things with like epoxide openings or ether formation, or another like fun one is like alcohols can become so many things now, and so you might have to turn an alcohol into a nucleophile and one to electrophile and join them together in various assorted ways. We could also say, okay, build this with only 2 carbon chunks or something. Like, we like doing little games. The synthesis questions hopefully will feel like a game, just a very stressful game because it's the exam. So again, with the timing, I know I have over here never spend more than 15. I would lower that. I would say never spend more than 12 minutes per question, because the number one thing that I see happen where students shoot themselves in the foot on this exam is they spend 45 minutes on the first 3 pages of box problems, and then they don't have enough time for anything else. The distribution of points is pretty even across the board. I think the mechanism, it's pretty even between all of the categories, and so like it's just not worthwhile to like try to maximize all your points in the box problems and then leave your synthesis blank. And I say that as someone who has left a synthesis blank on many a Orgo exam. But that's the general overview. My take on the exam, because we have a draft, I did it. I think that the box problems, there are a few that are like really straightforward, and then I think the box problems are really where it's a little bit more challenging. The theory reactivity I think is like straightforward. The radical mech I think is straightforward, and actually I think all the mechanisms are pretty, like we're not being severe on the mechanisms. Like you have to know it, you have to know your reactions and like execute them, but I don't think it's going to be like a blindsided, like I've never seen this before in my life kind of thing. It's like if you know the mechanism, you will do well on that question. If you don't know the mechanism, you won't do well on that question. And then the synthesis DCC I feel like is pretty easy. The other one I feel like is a little bit harder, but it's always kind of a toss-up. Y'all were much better on the first exam synthesis than like in past years, and so we'll see how it goes. But that's kind of the rundown of the exam and like my take on it and kind of what you're going to be asked. Are there questions generally on what you're going to be asked, or anything about the exam logistically, or anything here before we go on and start doing kind of practice-y things? Yeah.
This is like more of a question about a reaction, so kind of ask it now or
Later, probably. Yeah. Do you, yeah.
I'm sorry, I didn't know you were done answering that question.
Yeah.
But, and I don't know if you already answered it because I came a little late, but I know on the last one, I watched the video for it and you said you would update us if you're thinking of doing the radical and the DCC.
We're doing both the radical and the DCC tomorrow.
Thanks.
Yeah. Cool. So do you feel like you have a good idea of just like the format of the exam, what to expect, and kind of like what you're responsible for? Yeah.
Will the radical one be a mechanism, right?
Yes, it's only a mechanism.
And will it be similar to ones we know before, or will it be like a new?
I mean, yeah, like again, all the radical sits in its own kind of camp of the little puzzles. So I would say it's comparable to the radical mechanisms on the P set. Yeah.
Challenge ones or the
Challenge rooms. You're not going to get just the basic HBr, anti-addition, Markovnikov done. You're going to have maybe that and other things, or like it starts off different. Like But the radical ones also, like if you make your make and break list, you're going to figure it out. Like if you assign the carbons and do your make and break. And I think the radical mech is pretty straightforward. I think that they're actually some of the ones in the piece that were harder. Yeah. Cool. Okay. Let's see. Our first topic of the day, since we know it's coming, amino acid synthesis, DCC, all that jazz. Our goal is to make a dipeptide, 2 amino acids coming together with a peptide bond, also known as an amide bond. Now, generally speaking, we need 2 amino acids to do this, right? We're trying to bring together amino acids. But there are only a few things that we can do on this synthesis to make it more complicated or more engaging. Maybe that's a better way to put it. One way is, what if we didn't give you an amino acid? What if we gave you an amine and an alcohol? And then you would have to like oxidize it. And then it's a carboxylic acid now, so now it's amino acid. The other way is, you know how to build an amino acid from scratch using the Strecker amino acid synthesis, sorry. So this is a 3-step, and this is also like fully fair game for like mechanism too. Like in the past, we've just done the mechanism question be the Strecker amino acid synthesis from start to finish. But if you have an aldehyde functional group, then you can install a nitrile, hydrolyze it, and then you are at an amino acid. You install the nitrile and an amine here. With this, so again, you could have your starting materials in aldehyde, then do this, or we could even go back even further. We could be like, okay, we give you an alkene, then you have to do an anti-Markovnikov alcohol, then you have to oxidize that to an aldehyde, then you have to do Strecker, and then you have your amino acid. Again, we're just adding more steps either before or after, but once we start the like protection, deprotection stuff, that's like a pretty core steps that happen every time. I would be surprised if you didn't see the Strecker on the test. So once you have your 2 amino acids, remember Bach, we have to protect anything that we don't want to react. So we protect our amine with Bach, we protect our carboxylic acid as an ester. Then once our things are protected that we don't want to react, DCC will combine the things we do want to react. And then we have our deprotection. First we use TFA to remove Bach, and our mnemonic is TNFA hates chickens, Bach Bach. Then we remove our ester with base, typically. Base is preferred here rather than H3O+, because H3O+ can break your amide bond that you just so carefully made. Then after that, we can do like last steps, like once we've made this, so we can do transformations with the functional groups on the end, or occasionally there are side chain functional groups that can go on and do other reactions. One of my favorite moves, it's gotten shot down every year because it looks scary. One of my favorite moves is to just, at the end of the day, use LAH and fully reduce everything. And now it just looks crazy, right? Like it just looks like a long boy molecule, no carbonyls. Where's the peptide bond? I don't see a peptide bond. But Logan shot that one down, so. Yeah, what? I think it's cool. Yeah, when I said in my first draft of exam ideas, he said, "Oh, you devil, these are hard." And then he said, "I'm not doing half of these, right, easier ones." I said, heard. Good, yeah, great feedback, thank you. So with that, let's try out a longer DCC synthesis and practice 1 over here. So, and then I'll also kind of pull the room for what y'all want to do. Based on like the feedback, some people don't want time to work alone and instead just want us to do it all together. Some people do want the time to work alone. Yeah, if you want to work alone first and like, or alone / with your friends and things, and you want some time to like attempt it on your own, can you put up 1 finger? And then if you want me to just start to finish do it with y'all, then can you put up 2 fingers? I think the ones have it. Okay. So I will give y'all like 5 or 6 minutes. Remember, what are our first steps anytime we do a synthesis? Functional group, map carbons, brainstorm disconnections, related reactions. Good. Cool.
wrong situation, and anytime you want it to stop, I know I can treat you better than he can, and any girl like you deserves a gentleman. Tell me why are we wasting time on all your wasted crown when you should be with me instead? I know I can treat you better than he can. I'll stop time for you the second you say you'd like me to. I just wanna give you the loving that you're missing, baby, just to wake up with you. Be everything I need, and this could be so different. Tell me what you want to do.
Yeah.
'Cause I know I can treat you better than he can. And any girl like you deserves
Yeah. What do you mean? I'm just trying to emphasize that the Strucker is a 3-step process. So yes, you totally can. Yeah.
Can we do it in one step, like on a sequence of like 1, 2, 3, 1, 2, 3, or just like draw the
You can-
like nitrile?
I think it would be good to draw the nitrile in the middle, but I think you can do it on 1, 2, 3. Just make sure if you are doing it that way, there are fewer opportunities for partial credit. So make sure that you are correct.
Just know that you don't have to do this alone. Promise I'll never let you down. 'Cause I know I can treat you better than he can. And any girl like you deserves a gentleman. Tell me why are we wasting time on all your wasted crown when you should be with me instead?
Truly,
I
yeah.
know I can treat you better than he can.
Oh, Lincoln.
Look at his move.
Do your synthesis for now. Yes.
To protect. It's ROE.
Can I ask you one quick question? It wasn't the practice test that it was dealing with H3O plus,
Yeah.
and it was like to build nucleotides, it didn't have the neutralization. Do we need to worry about that?
Can you show it to me later?
Okay.
Like, can you show me the actual thing where it doesn't have that? Yeah.
Okay.
I know people are not done, but would now be a good time to try to pick up the pieces and put it together? Let's see. Do we have any amino acids in our starting material? No. The left one, is it closer to amino acid? What do we need to do to it to make it an amino acid? Yeah. We have our amino. We need to make our acid. So we use chromium with who? Say again? Water. Yeah, great. So that makes H2 and blah, 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 OH. The other one, we're not even close, right? So we probably need to Strecker it. So Strecker starts with what functional group? An aldehyde. So how do we make an aldehyde? Chromium with who? Pyridine. Okay, then we do our Strecker. So this is the thing, and I got a question. Can you do all 3 steps on the arrow? Yes, but make sure it's correct, because then it's harder to give you partial credit if it's not. I'm going to do it correctly, so I'm going to put it all on the arrow. 1, NH4Cl, NaCN, 2, H3O plus, 3, neutralize. So, with that, I'm going to draw it suggestively like our product down here. Excuse me. There you go. So I'm seeing where these carbons are in the product, and I'm just drawing my amino acid to look like that. Okay, so now let me think. I want the carboxylic acid of this one to react down here in my amide. I want the amine of the other. So I need to protect the things that are not in purple. So I protect my amine up here using who? Bach. What's the actual reagent name? Bach2O, great. Then I protect this one as an ester. What's your favorite alcohol? Methanol, sure. Meo, also known as home. H-O-M-E. Bum bum bum. O-M-E. Okay. Now it's time to combine. So we have our reactive boys. We have our protected boys. So sheltered, protected. I need to write the actual Bach here. Then I do combine. DCC. Exclamation mark is optional. We get NH Bach down here. 1, 2, 3. We have our amide bond. So we still have our protected boys, so we need to deprotect them. So first I'll use tenofame. Then I'll use NaOH, followed by H plus workup. What if my final product, instead of this, what if it was with chlorine here? Then what would my next step be? Yeah. Okay, and then what if this was another amide or something? Well, then I would have to do, like, first I would have to leave this amine protected unless I wanted to attack itself. Then I would have to do, like, acid chloride to amide, or I would do another DCC. But, like, you can see how we can, like, tweak, add on little things. What if I had, like, an aldehyde at the end of one of these, and then I added this boy to it? H plus. Then it would become a acetone. So, like, the only ways that we can really make the DCC harder is more steps at the beginning or more steps at the end.
How do we add the aldehyde to the end?
Oh, I'm saying what if there was an aldehyde there all along?
Okay.
Sorry. Yeah, y'all don't know how to poof an aldehyde out of an alkane. Cool. Any thoughts or questions on this? And you see how this quickly became like a 12-step synthesis just because of all the protecting, deprotecting, Strucker steps. So these, I think, often look quite daunting. Yep.
Could you, for some reason, like, use the starting molecule on the left twice?
Yeah, to not make the product, you could. Yeah. like that's exactly why we protect. So like if we did not protect this one over here, and we did protect this one even, then sometimes it's going to join the way that we want it to. Other times, two equivalents of this molecule are going to join with themselves. That's the whole point of DCC. If we don't want it to react with itself, we have to protect at least one side of the molecule. I was also trying, when I was like drafting exam questions, I was like, can I make a dipeptide that was cyclic? And the answer I came to was no. Because of this, it's going to react with itself thing. Instead of cyclizing, it could just react with another equivalent of itself. Mm-hmm.
Could there be one where you're asked to do like this same, like make just one molecule and protect it, like protect two of that molecule in different ways so that...
Hypothetically, but y'all can't have like a 15-step synthesis. Yeah. And again, the big things we want you to know are the Strucker synthesis, protection, deprotection, that kind of stuff. Okay. Let's see what else there is. So while we're in Lecture 5 land, let's talk about other common Lecture 5 reactions. Amines and enamines, you should know the mechanism, you should know the fake mechanisms. But today I'm going to make sure you know the fake mechanisms. So if you're given an amine, how do you get back to the starting materials over here? You cut the CN double bond, put a carbonyl on the carbon side, and add H's until it's neutral on the amine side. If you're given an enamine, locate the central carbon that's connected to the alkene and the amine, cut the bond. On the amine side, add H's until it's neutral. And on the carbon side, pave over the double bond, add a carbonyl. Are you ready to do it? Let's do disconnection. So, disconnection number 1, amines and enamines. I've given you an amine, I've given you an enamine. Take all of 45 seconds and disconnect them. And that is 45 seconds. Wow. So I'm going to start with the amine because it's easier. Chop in the double bond. On the carbon side, make a carbonyl. On the nitrogen side, add hydrogens until it's neutral. Enamine, find the central carbon, cut the bond. On the carbon side, pave over and add a carbonyl. On the nitrogen side, add hydrogens until it's neutral. What type of amine is this one? Primary or secondary? Secondary. What about this one? Primary. Great. Secondary amines make enamines. Primary amines make amines. Okay on the disconnection? Cool. Then going back to lecture 5 things. We also have our redox line reactions. Y'all seem to pretty much have down the which sidekick of pyridine or water. The only other thing I'll say is, let's say for a synthesis like this one, what if I gave you an aldehyde to start, but you wanted a carboxylic acid? You can use the same reagents here. You can go aldehyde to carboxylic acid with chromium and water. So that's one that students forget often. Then in terms of the reductions, LAH is our reduction bad boy. And I'd just like to point out that if you are forming an amine, you've used one of these reactions. These are the only real reactions in the course that make amines, other than the amine, enamine hydrolysis, but those are like pretty obvious. So here we can reduce an amide, or we can reduce a nitrile, and those give us amines. We have our CAD interconversions. So our general rules of thumb is everything can become a. Great. And it's easier to go down in reactivity than up in reactivity. So carboxylic acids are grand central. These are great ones both for line reactions, box problems, and mechanisms, just because those are a little bit longer mechanisms. The mechanisms that I think are like most likely to show up of the CAD family are I put in green. These are the ones that are the most like interesting. Then the other thing is on the theory front, you could be asked to rank CAD reactivity. And the ones people forget about often are acid anhydrides. These are second most reactive after the acid chloride. You don't know any reactions of her, but she has a lot of reactions. She does a lot of similar reactions to everything else. There's another version of this web where there's an anhydride girl here, and she's well connected. She has a lot of friends. Then our least reactive is the carboxylate. Why is the carboxylate not very reactive? Resonance, and specifically the resonance's structures are completely equal. So this is only like 50% of the time a carbonyl. Then nitrile, the triple bond is less reactive, and it's a pi star CN, and then we have amide. But that's basically all I have to say on lecture 5. I don't think there's like a ton. So. Lecture 7. Lecture 7, we had our Making Alcohols Leave family, and I think I saw a lot in, like, help room. People really want to throw their precious molecules in boiling acid. Like, people really want to use, like, concentrated HBr in heat and boil off an OH. And I get the instinct. You're like, oh, protonate, better leaving group, leave, yes. But if we have anything else interesting on the molecule, we can't use that strategy. So if you are trying to get an alcohol to be a leaving group, these should be your main strategies. And with these, our big choice is, do we want it to invert stereochemistry, or do we want to retain the stereochemistry? Retaining, we use Tosyl. Inversion, we use the halide ones. We also have our synthesis strategy of if we want it to overall look like we are retaining stereochemistry, like starting on a wedge and on a wedge for our overall like substitution, then really what we're doing is 2 SN2 steps. 1 SN2 step with our leaving group, and then 1 with our actual nucleophilic attack. However, if we want it overall just to look like an inversion, then we've done 1 SN2 step, so we use Tosyl to retain. Other things in lecture 7, epoxide opening. So, you know, whether it opens an acid or base is important, which side it attacks. Also ways of making epoxides, either directly from an alkene with MCPBA, or we can make it from a halohydrin with NaOH. The other thing is epoxides and alkenes are the 2 functional groups that we associate with having a situation where you have 2 reactive sites right next to each other. So we saw this a lot in the problem set where we had to think about, oh, okay, one of these carbons reacted with another carbon, but now it's plain. The other carbon like has an ether on it. I think that was your like P set. And so that's 2 reactive sites. Even if one of them is an alkane in the final product, it made a carbon-carbon bond. And the only way that you can do that where there's not an actual functional group is this Grignard to an epoxide. But otherwise, if you're seeing 2 functional groups in a product, it probably came from an epoxide or an alkene. I also want to talk about ways of making ethers, my least favorite functional group, mostly just because we said, oh, there's the SN1 way, the SN2 way. The gold standard, the first thing that you should check if you're making an ether is probably Williamson ether synthesis. NaH makes an alkoxide, and then you do an SN2 backside attack on this ETBr or whatever alkyl halide, and then you have an ether. We also have that SN1 way with if you have a tertiary alcohol, and then for when it's an ether, one side of it has to be primary. So this alkyl halide always has to be primary. But that's kind of what we talked about in lecture 7, but then some more ways of making ethers popped up. So we have epoxide opening. This one I just did it in base, but we could also do or in acid. Then we had some ways of making it from alkenes, like we could do an alcohol with H plus or an alcohol with Br2. That would make a halo ether if we did it with Br2. This one could rearrange because we do H plus. There's one other way of making an ether with alkenes, and it was just the mercury HgOAc2 with an alcohol in the first step, followed by NaBH4. And that's going to make our alcohol here that didn't rearrange, if there was a rearrangement option. So we just have a lot of ways of making ethers, and I think it's kind of nebulous. So I wanted to do kind of a roundup of some of the bigger ideas. The ones I have in print are the ones I think are the most important. But yeah, I think for completing this is all the ways that we can make an ether. Also connected to ethers is something that we haven't done very much of, which I wanted to plug before the exam. Hint, hint, cough, cough. So we didn't do much with breaking open ethers. I basically said we can boil them in acid, which, yeah, it's not ideal, but ethers are not that reactive, so we have to boil them in acid. We don't have another choice. So what we would do is, like for this one, a primary ether, put in HBr, you first protonate the ether, then bromine comes and does a backside attack. Then we have one bromoboy after the attack, and one alcohol. But our alcohol, we're still in concentrated HBr, so we can protonate it yet again, OH2+, and then do another SN2 attack, and now we have another alkyl halide. So if you have a primary ether, you wind up with two alkyl halides at the end of the day, and this proceeds through like an SN2 mechanism. If you had some of them tertiary, if it was both tertiary, then it would be the same kind of deal, but it would all be SN1. The leaving group would leave, then the bromine would attack the carbocation, and that would happen on both sides. However, if you have one of the sides as secondary, then you get a weird thing. So if you have a secondary primary ether, you again protonate, and then you're going to do a backside attack because that's the fastest, and you're going to do it on the primary side. With that, you get one alkyl halide, but then your alcohol just stops. It doesn't go on and make another alkyl halide. So why does it just stop? It's not very good for SN2. It's not very good for SN1. So primary and tertiary sides are always going to become alkyl halides, and then secondary sides will stay alcohols. Yeah.
What's the leaving group if it is 3' 3'?
It is plus, and then this whole thing leaves.
Okay.
So that would make carbocation and then alcohol. And then the bromine would come in and attack here. And then we would do the same thing over here where we would protonate it one more time. This would just leave as water, and then, yeah.
It doesn't matter. I just find it confusing because both sides are the same, so I
Yeah.
don't necessarily know why I would leave one.
Yeah, well, because they're the same, either could happen, you know? I tried to do a box problem with this that Logan said was too hard. So the box problem is a little bit easier. But to practice this new skill, let's do another disconnection here. I've given you a couple of ethers, and we're going to boil them on the stove. So I want you to draw what the product is, remembering which ones get turned into alkyl halides versus alcohols, and then predict whether the mechanism proceeded via SN1 or SN2. And I'll give you like another 45 seconds.
Obviously, we're at the beginning of something. I don't expect you to know where it's gonna go, but I believe we might be on to something.
Okay, so the top one's primary. I cut. Then I put alkyl halides on both of them. And then for this one, primary is it SN1 or SN2? SN2. Next one, I look at this, I have secondary, tertiary. So the secondary one's going to stay in alcohol. And the tertiary one is going to become an alkyl halide. And this one is going to be SN1. Cool. Any questions on your ether disconnection?
What would the oxygen on the top one?
It would leave as water. Yeah, it gets kicked off in the boop. There she went, water. Cool. I think that's all for lecture 7 things. So let's see. Lecture 6, substitution elimination. What's the most important thing we care about for SN2? Yes. We're going to need a little bit more energy. What's the most important thing we care about for SN2? Yes, E2? SN1, E1? Good, okay. If we see conc H2SO4, what are we thinking? E1. What's the trap with conc H2SO4? The things to watch out for, trap for, there's a case where conc H2SO4 is not E1. What is that case? Say again? No. What if what if we have, let's say, our alcohol over here, and we have another alcohol on the molecule?
The alcohol can attack.
Yeah, we could protonate this one, it leaves, and then this one does an intramolecular attack like SN1 style. So it's only like ensuring that we have E1 for the conc if there's no other nucleophile around. If there's any other nucleophile around, it can do SN1, and SN1's faster. If we're tied between SN2 and E2 and they're both good, who wins? SN2, why?
It's faster.
It's faster. Cool. SN2, what should we be thinking about stereochemistry-wise? Stereochemistry-wise. Inversion of stereochemistry. We're always doing those backside attacks, so we always need to make sure we're swapping dashes and wedges, things like that. E2, what's our requirement geometry-wise to do an E2 reaction? Yeah, so our leaving group and the beta hydrogen need to be anti-periplanar to each other. Yes, the other thing to watch out for with carbocations is, remember, if our carbocation is stabilized by resonance, it's even better than tertiary. So like a classic one that trips students up on the exam is like one of these. So if we have this, it's going to be this carbocation, which is not primary, it's allylic. It's next to the alkene, so it's quite stable. It's going to be a great candidate for SN1E1. Then, yeah, remembering alcohols versus alkoxides. Alkoxides are good nucleophiles and strong bases. Alcohols are not. Oh, yeah. So if we can make multiple different eliminations, which one wins? Like, let's say if I used Naomi. Are we forming an internal or a terminal alkene? We're forming an internal alkene. And that internal alkene, is it going to be cis or trans? Trans. Why? It's more stable. Why? Sterics. Okay. Yeah. If it's cis, the two ends are going to bump into each other more. However, what if we want to make the terminal alkene? What should we use? We should use Katbu. And why does Katbu make the terminal alkene? It's bulky, and so it would prefer to grab a hydrogen from the very end of the molecule. Great. So a few of these on the exam are going to be straightforward, but most of them are going to be like tricky. They are going to have like the more complicated things. So it would be nice if there was a sheet somewhere where all the ways that it could be complicated are compiled into one document. Wouldn't that be a nice resource to have? Maybe a sheet that we could call what to expect when you're expecting substitution elimination reactions. That could maybe be the last page of the Section 6 handout, maybe. But at this point, it's too late, so. One thing I did want to mention in case you see it on the exam, which honestly I don't remember if it comes up anymore, there is one case where solvents actually kind of matter. And we did not really tell you much about this. And so that's why I wanted to like talk about it here explicitly. If you are tied fair for everything, notably if you are tied fair for SN1 and SN2, you can control which one it does by your solvent. So if you use a polar protic solvent like water, that is going to be favoring SN1. If you use a polar aprotic solvent like DMSO, that's going to favor SN2. The other thing is like this acetate is our nucleophile here. And let's imagine this acetate in a polar protic solvent. So it has a negative charge on this O, right? And if we are in a polar protic solvent, we have hydrogens that have partial positives on it, like this. Partial positive, partial positive, partial positive. And so the way I think about it is the nucleophile has groupies here in the like polar protic solvent. So if this nucleophile has groupies, is it going to be as good of a nucleophile in terms of being able to attack the electrophile? No, because it's crowded. And so because the nucleophile is not as good in a polar protic solvent, there's more time for the leaving group to leave and make a carbocation. So it favors SN1. However, in a polar aprotic solvent like DMSO, you have like partial negative charges, but you don't have any partial positives on the hydrogens. And so there's no crowding the nucleophile, and it's easier for the nucleophile to just do like a little backside attack. And so it favors SN2. Again, the upshot of it is DMSO means SN2 for y'all's purposes. Some classes, again, get very into the solvent effects. We don't care as much. The other thing I wanted to flag over here was on the base strength. So, like if I said HOME, is that a good, fair, or poor base? Poor, because this is the neutral alcohol. What about Kotbu? Is Kotbu a good, fair, or poor base? Good. It's a really bad nucleophile because it's bulky, but base is not about like bulk. Base is thermodynamics, so it's still a good base. What are examples of our fair bases? CN, what else? SH. Anyone else? We have our acetate, and then I think they also put NH3 here. These kind of are the only ones to really watch out for in the middle. Typically, y'all get the good and the poor, but these fair ones can sometimes like come out of left field. Cool. I think that's most all I have to say about Lecture 6 stuff. So for Practice 2, I've made essentially another first page of an exam. This one only has 4, whereas the first page will have 5. But try out substitution elimination, GFP things. These are tricky problems. These are exam level problems. So I will give you some time to work.
take my pearl. 'Cause my bed is on fire. Mama, I'm so scared. Will you ever like this? Once you went out on the edge, just spin around.
Surprised. There are a lot of people that are like,
He's saying a prayer.
do y'all want one more minute to like try some problems, or do you want to do them together at this point? Let's talk through them. So the first one, I see a ring. When I see a ring on the first page of the exam, I'm thinking E2 on a ring, but let's just do the ranking just to be safe. SN2, are we good, fair, or poor? We are fair, and I would say fair minus because we're secondary on a ring. What's our base strength with OET minus? Good. S1E1, fair. So E2 wins. We draw our little mini chair. We want our leaving group, the tossle, to be axial or equatorial? Axial. Okay. Well then over here we have a hydrogen up, a methyl down. And then over here we have a hydrogen up, a deuterium down. So the one that's antiperiplanar is the deuterium. So we are doing an E2, and our product is her. And you can write in the H if you want, just to be clear that we removed the deuterium. But if you're not thinking through the antiperiplanar stuff, the most common answer I will see on the test when grading is this. Because why? Why is this an attractive option if you don't have to think about antiperiplanar? This is the most substituted alkene that you can do. So it follows Zaitsev rule. So you would think, if you're following Zaitsev's rule, this is the one that works. But why can't we make a double bond over there? We don't have an antiperiplanar beta hydrogen. Okay, next one. So SN2, are we good, fair, or poor? We're secondary, so we're fair. And then do we have an OK nucleophile? Not really. So I would say like fair minus. E2, HOME, good, fair, or poor base? Poor. Yeah, just an alcohol. It's like water. SN1E1, secondary, I'm thinking fair, but is there anything else going on? Yeah, there's resonance. There's this double bond. So we're going to make this carbocation. And then, is HOME going to go in and attack? What else is there going on? There, we have an intramolecular attack. So it's going to make a 1, 2, 3, 4, 5, 6-membered ring with an oxygen. 1, 2, 3, 4, 5, 6. And then on 6, we have a dangling little boop. So the other thing that we have to think about is we have to think about stereochemistry. Did we make any stereocenters in this? This is the stereocenter right here, right? We're attached to 4 different things. So what do we need to do here? Well, we need to put it on a wedge or a dash and do a plus minus. Why can it be either of them? What's the thing that makes it could be wedge, could be dash? Carbocation. We can attack the top lobe or we can attack the bottom lobe. Great. Okay, so this one was great for SN1. This one down here, SN2, E2, 1. So, I have 2 potential leaving groups. Are they both primary, both secondary, or are they different?
They're both primary.
Yeah, this is kind of weird, but remember, deuteriums are just like hydrogens, so if we kind of implied them like hydrogens, they're both primary. So, who's going to be the one that's the better leaving group? Bromine. Why? Bromine's bigger, so when you kick it off as a negative charge, it spreads off that negative charge in a big beach ball. And so it's like less angry with the negative charge. So we're going to analyze the bromine as our main one. So SN2, we're primary, so good, fair, poor? Good, because we're primary. E2, we have NaCN, are we good, fair, or poor? S1E1, we're primary, are we good, fair, or poor? Poor. So SN2 wins. We're going to do a backside attack. So I'm going to leave this left side totally alone. And then over here, I'm going to do the version where I put everything in the same spot. I swap the wedges and dashes. Do we get a mixture of stereoisomers for our product? No, because we did specifically an inversion at that SN2 site. Okay, last one down here. We're conking it, so what do we think? E1. Let's do our analysis just to think. SN2, E2, 1. We have an alcohol, which is already a bad leaving group, so but it is tertiary, so poor. E2, we have sulfuric acid, so poor. SN1, E1, we're tertiary, so we're good, but more than that, what else are we? This carbocation is tertiary, but we also have resonance, so it's like phenomenal. It's probably the best carbocation you'll see. So we have our benzene ring. We have our carbocation down here, and then we have our ethyl, and we have our methyl, and a hydrogen. And we're going to do an elimination, make an alkene. Now, when you're doing E1, you don't need to do all this rotation to line up antiperiplanar and all of that, mostly just because you can either interact with the top lobe or the bottom lobe of the MTP orbital. So we're just going to form the most stable alkene. Is the most stable alkene going to put the ethyl cis, or is it going to put the methyl cis? Yeah, I asked that question poorly. We have to put something cis to the big phenyl group, and I'm saying, do we want to put the big ethyl cis over here, or do we want to put the big ethyl trans? Trans. That's a better question, sorry. So we do this, and we get E1. Cool. I mean, yeah, but we have the most stable carbocation. Yeah, like, I mean, we should in the sense of, like, checking to make sure that it can't get more stable. But if it's resonance stabilized, you're not really going to get more stable. Yeah. Okay, any other questions on these? Okay. We're to everyone's favorite lecture. Lecture 8, alkenes. So many choices. What a beautiful time to be alive. Alkene regiochemistry. All of our reactions are Markovnikov except for 2. And by Markovnikov, we're talking about Markovnikov's rule, which is that the more electronegative group gets added to the more substituted side. How do we mess with that? What are our 2 reactions? Well, we could do a radical bromination, HBr ROR with delta. That will add a bromine to the less substituted side. But what's the issue with that? Why is that not our, like, safest route?
Radicals do funky things.
Yeah, radicals can, like, open up rings and close rings, and yeah. So what's our only safe option for doing anti-Markovnikov addition? Well, it's anti-Mark, anti-John, John Tucker Must Die, which is a movie on HBO, hydroboration oxidation. Obviously. So hydroboration oxidation is kind of our gold standard for doing anti-Markovnikov addition. And we add an OH, anti-Markovnikov. In terms of alkene stereochemistry, we need to know whether the reactions syn, anti, or mixed. And for syn, we are adding to the same side of the double bond. For anti, we're adding on opposite sides. And for this, there are a couple of ways to write it. One of them is more useful when you are writing your products. One of them is more useful if you are trying to predict the starting materials. So, like syn, if you're writing your product for either of these, it's easiest to put your things on wedges and dashes. But if you are trying to go backwards and like see what the alkene was, you are going to have a box problem where you have to do something like this and go backwards, similar to the challenge problem on the last P set where you were doing this. If you have a syn reaction, then it's easiest to put the 2 things that you add in the plane. Once you do that, then the things that are on wedges were cis to each other in the original alkene, and the things that were on dashes were cis to each other in the original alkene. And that's kind of the easiest rule. You can make rules over here. You can make rules like, okay, here, syn, if it's in the plane, then those are cis, and their dash, they're cis. But it gets funky for anti. For anti, if you do this in the plane approach again, then you still have the wedges are cis, the dashes are cis. So that works out. However, if you do it over here, then your rule has to be like the things in the plane are cis, and then the other wedge and dash are cis, and that's just a little confusing to me. This is the easiest way for me to kind of think backwards. And so you'll probably have to be given a product and rotate it into one of these positions based on whether it was a syn or anti reaction. And then you'll get what the stereochemistry of the alkene was at the beginning. I also made a little chart of like syn-anti mixed of our reagents just to kind of visually organize it and see them all kind of laid out. So we have a good kind of like smattering across the board. And then, what is practice 3? Oh, practice 3 is alkenes. We're going to do that. So we're going to see this thing in action over here. This probably felt a little nebulous when I was talking about it. So we're going to do these together for practice 3. So the first one is we are given a product and we have to predict a starting material. And I have a typo in this, so sorry. This H should be a methyl. Okay, so when we are doing this, what we have to do is we have to clock the reaction on the arrow, and is that reaction a syn, anti, or mixed reaction? B or 2, HO and me. Anytime we have a halide, it's going to be anti. And what two things did it add? Well, we definitely added a bromine, but did we add a second bromine, or did we add something else? OME. Cool. So we have these two added. So we know our double bond needs to be here. We just need to make sure that we get the right stereochemistry of the E versus the Z alkene. So what we are going to do is we are going to rotate it so our bromine and our OME are in the plane and anti to each other. So the bromine's already in that position. So I can put the methyl here, the hydrogen here. That one's good. But for this one, in order to make my OME in the plane and up, I need to rotate my ethyl down and on the wedge, which means it's going to rotate the methyl back on the dash. So now we have our anti-orientation here. So we know the things on wedges, the methyl and this ethyl, are going to be cis, and the things on dashes, the hydrogen and methyl, are going to be cis. So what I do is I draw my double bond, I put a methyl and ethyl cis here, and then I put a hydrogen and a methyl cis over here. And so we have the kind of yellow side and we have the purple side here. We also have to think about stereochemistry when we do E2 in the forward direction, when we don't have options for our hydrogens. So like for this, you see we have Naomi. We definitely are going to want to make this internal alkene here, but do you see how we only have one hydrogen present on that carbon? When we are in this case where we only have one hydrogen present, we have to rotate and see the antiperiplanar of it all. So there are two ways to do it. I could do one way that's like this, where I rotate the molecule. I could do another way that's a Newman production. Which would y'all like to see? The Newman production or the rotation? I've gotten a couple of rotations. Is that okay? Cool. So what I need to do with this is I need to rotate it so my hydrogen and my leaving group are anti to each other. So I'm going to put my chlorine up in the plane and the hydrogen down in the plane. Neither of these are good in their current position. So this is one where actually a Newman production could be a little bit easier. Again, it depends on your comfort with these different skills. So I'm going to rotate this hydrogen down in the plane, which means that this methyl gets rotated up on the dash, which means the ethyl comes on the wedge. For chlorine, it's a little bit more subtle. For chlorine, right now my chlorine's going towards you, and now it needs to go up and in the plane, right? So I'm doing a kind of rotation in this direction. So chlorine going towards you, up and in the plane. Then what happened to that hydrogen that was originally here? If I do a rotation, again, chlorine up in the plane to here, the hydrogen goes from there to there further back. So it's still on a dash, but it is down dash versus up dash. Similarly, the methyl that was originally in the plane here, I'm going to continue that rotation because we've been rotating in this direction. I'm going to take the methyl here, and now it gets rotated forward. So now we see clearly our anti-periplanar beta hydrogen leaving group. And we have a scenario here where the ethyl and methyl here are cis, and the methyl and hydrogen are cis. So ethyl, methyl, cis, and these are yellow ones. And then methyl, hydrogen, cis. This is the hardest stereochemistry that you'll have on the test. Like, it's the hardest skill. It's the one that requires the most rotation and everything. And you're likely only going to have one or two box problems on it. You're definitely going to have a reverse one. I don't remember if you have a forward one or not. There at least was one in some of the draft. But this is the hardest skill. Questions on this? Yeah?
Are you still allowed to like bring like from the lab?
Hell yeah. Hell yeah. Hell yeah. And honestly, the one that I use for this, I have it with me. It's the same one that I use for the meso. It's the one where it basically has two stereocenters right next to each other. This is really great for, like, let's say it's a SIN addition or something. I see these blue ones are on wedges going towards you. So what I can do is I can just take these green ones and fold it in, like it's an alkene, and the ones that were towards you are now cis on this like little fake alkene once I folded it. So again, these were cis towards you. I have my SIN things here in green, and I'm gonna fold these in so it kind of looks like an alkene, and that's how it collapses. Oh. We're gonna keep on chugging. Wow. Oh my gosh. Other reactions in lecture 8. So we can make alcohols in various assorted ways. H3O plus is fine and dandy, but what do you have to watch out for? Rearrangements. HGOAC gets around it. It does Markovnikov, no rearrangement. And then finally we have our hydroboration oxidation that is anti-Markovnikov. You'll know my like bad mnemonic for like why the mercury does no rearrangement. It's real smooth brain. It's not as smooth brain as the like John Tucker Must Die HBO one, but it's like we don't want a rearrangement. We want order.
Oh.
Astrology, planets moving in a line, ellipses. Ellipses. Yeah, they move in elliptical orbits. But I'm like, order. The planet's not jumping around. Mercury. Mercury's a planet. It's also an element. Mercury. Thank you for coming to my bad mnemonic talk. Thank you. Come up with a better one, please. Oh, okay. So then we have the Wittig reaction. She's powerful. If you don't see the Wittig on the exam, you have not done well. Sorry. Like, it's just straight up gonna happen. Like, it is like one of the most useful reactions that we have because it's one of like 4 ways that we have total of making carbon-carbon bonds. It can glue 2 molecules completely together. One of them as a ylide, one of them as an aldehyde, and then it makes an alkene. Other than elimination, it's the only other reaction that we know that makes an alkene. You might have to make an ylide from scratch from an alkyl halide. Or if you are just supplying it on arrow, you can build your ylide. It depends on like if you were in a synthesis and you had to use the starting carbons and turn it into something else, you could have to do this formation of an ylide step. The one thing to like clock with that is when you do this first step is SN2. And so you typically want your ylide to be the smaller side, the like primary side, rather than like a secondary or tertiary. The Wittig is also our most useful way of making terminal alkenes. Specifically, making a terminal alkene and adding a carbon is really useful. Because here we could have formaldehyde as our carbonyl, and we could have our normal ylide, and that's just going to add a single carbon down here like this. Or we could have a single carbon ylide, and that's just going to add a single carbon over here like this. So with this, let's practice the disconnection really quick for the Wittig. What we're going to do, and we're going to do this together, is we find our double bond, cut it. When we cut our double bond, we need to make one side a carbonyl, one side an ylide, and we have options, right? We could make the top one the carbonyl or the ylide. So let's do both options. Option 1, the top one's the carbonyl, and option 2, the top one's the ylide. To make your ylide, literally where you cut, draw a line to PPH3, put a plus on it, a minus on the carbon above. Then, for the bottom, it's the other one in each case. So over here on the right, it's the ylide. On the left, it's the carbonyl. So now, which one is going to be preferable? Is it going to be preferable to have this ylide, option A, or this ylide, option B?
Option B.
I see there's discourse.
SN2, so it would be
So because we have to make this from an alkyl halide, doing SN2, it's easier to do the backside attack here, where it's primary, than it is over here. You would be doing SN2 on a secondary. That okay? Mm-hmm. So, preferred. If you did the less preferred one and it still worked, you'd be okay, but like, we are typically not going to do that or intend for you to do that, so maybe that's a hint for which to do. Going back, in lecture 8, we also had this other powerful reaction, ozonolysis. Ozonolysis is our oxygen scissors. It splits things open. So it can take one molecule and split into two, or it can take a ring and bust it open. Ozonolysis you don't need a mechanism for, but you should be able to draw the products. And the kind of big idea I want to introduce here is ozonolysis is kind of the reverse of the Wittig. Wittig glues things together, makes a double bond. Ozonolysis cuts a double bond, makes two things. So they really are kind of most powerful heavy-duty tools for moving around some molecules. Cool. So with this, we have some general box problem practice, and then we have lecture 9 things. But I think I want to cover lecture 9 stuff before we do all the mixed practice together. Any questions on lecture 8? The time has come for lecture 9. A lot of theory, a lot of content, several reactions. So, lecture 9, I put it here, but you all really learned this in lecture 8. Radicals. If you're not making a make or break list, I don't know what to tell you. Some people can just see it and they don't need it, but for me, I need a make and break list. I need to number my carbons, map them on, make a make or break list. From what I remember of the radical one I chose, I think it should be pretty easy to map the carbons. Like, I don't think it's going to be like a super challenge. And so it's a thing that I think you all have potential to get full points on the radical question. If you number your carbons, make your make and break list. Other things. You don't have to draw termination steps, but you do have to draw initiation steps. So those first steps with HBr, ROR, all the things, and when you're making your own radicals, that should be easy points that you are like locked and loaded on, and you can like do the initiation like 20 seconds, and then you can do the actual like harder mechanism. But yeah, I'm not going to do this guided radical analysis. It was literally just talking through one of the ones from the problem set. I think that the section stuff that we've done on the radical analysis together is probably easiest or the best. Okay, then we have the concept of EAS activation. So anytime we have electron donating groups, we activate the benzene ring, make it more reactive to do EAS reactions. And when we donate, we can donate electrons via either resonance or hyperconjugation. When we withdraw electrons, we deactivate, and we can withdraw via resonance or induction. So with this, you should know kind of what's a strong activator versus moderate activator versus a weak activator, because you probably will have to rank these. So like, for example, imagine all these are on a benzene. We have A, B, and C here. And actually, I'm going to do one more. D. Of these options, which of these are activating? B and D. How do we know? Well, these are the ones that have a lone pair that could donate into the ring, donate via resonance. So the other ones are deactivating, right? Now, over here, between B and D, which one is the stronger activator? D. You were locked and loaded. Why?
Like the resonance only has one direction it can go in?
Yeah. I sometimes describe the lone pair here as like in a poly relationship with the ring and the carbonyl. Of it could donate into the ring and activate the ring, or it could donate into the carbonyl. And because it's split, it's not as good of an activator. Whereas this one, it's only one direction, so it's the better activator. Cool. The other thing with this, with activation, is remember that nitro groups and sulfonic acid groups are so strong, strongly deactivating, that you can't do Friedel-Crafts. You can do other things. You can do brominations, you can do sulfonations, another nitration, but you can't do Friedel-Crafts after you add that on. Aromaticity, knowing your 4 requirements, cyclic, planar, continuous, and 4 n plus 2 pi electrons. For this, you really have to, at a fundamental level, know the hybridization of all of your atoms that you're thinking about, and know each of the orbitals where the electrons are in. So, this top one has 2 lone pairs on it. These have 1 lone pair. This nitrogen has 3 electron domains, so it's sp2 hybridized. It has a single p orbital. Is this lone pair in a p orbital? No, because its p orbital is being used in this pi bond. So this lone pair is in sp2. So do we count it towards the pi electron count? No. Over here, this has 4 electron domains, has a lone pair, appears to be sp3 hybridized next to a pi bond, so it's sp2 by the neighbor rule. It has 1 lone pair that is in a p orbital, because we only have 1 p orbital. So 1 lone pair is in a p, 1's in sp2. But you have to like know that, and like you can get quicker by doing this over and over and practicing it. But like in order to determine whether you include the electrons or not, that's something that you need to know. Also remember, like if we had like boron, what's this molecule? So, are we cyclic?
Yes.
Are we planar ostensibly? Do we appear to have continuous p orbitals? Boron has an empty p orbital. That's the tricky one where I was like, let's plug that. And then how many pi electrons do we have? 4, because remember, boron's is empty. So is this aromatic or anti-aromatic? Yeah, this thing doesn't want to exist. We also have this idea of exocyclic pi bonds. So I had like an infographic in the notes, but I didn't really talk about it. Basically, whenever we have a pi bond on the ring but outside of it, it is ambiguous. It is automatically non-aromatic. And so if you want to determine whether or not it could be aromatic, what you have to do is you have to ionize it. So you have to do a resonance structure here. And your resonance structure with this, it's always going to go to the more electronegative element. I couldn't just choose to make it go this way. Like, that's not going to happen when nitrogen and carbon are sharing electrons. So if I do it this way, I see now this is a carbocation in the ring. We have 6 pi electrons, and so it would be aromatic. So if this molecule has the choice between being non-aromatic and aromatic, what's it going to choose to be? Aromatic. So that would be the correct answer. If we put this molecule on the test, we would want you to do the resonance and call it aromatic. Because overall, if it has these options, it is aromatic. Over here, this one, we have 2 of them. If we drew the ionization here, we see these are both carbocations. We have 4 pi electrons, so this would be anti-aromatic. So if this molecule has the option between both of these, what's it actually going to be? Non-aromatic. Anti-aromatic is super unstable. We never want to be that. And it's so easy for this molecule to avoid it by not having much ionization character for these bonds. Slide. Last things here are directing effects. So remember, activating groups direct orthopara, deactivating groups direct meta, except for the halides, which are, oh, do I have the sound cue? Is it nearby? Can I get to it? Oh no, they are.
Darling, you are
The halides are deactivating, but they direct orthopara. So that's the only weird one with the rule. Other things that you should be thinking about is the resonance to kind of explain why these are directing the ways they direct. If you have 2 things on a benzene, they both have directing effects, and you have to consider both of them. So here, if you have an electron withdrawing group, it's going to direct meta to it, so ortho-meta here, and ortho-meta. And then this one's an alkyl group, so it's going to direct orthopara to it, orthopara. Here they agree. Yay. We love agreement. Good. On the other side, you have both of these that are electron donating groups, but they're each going to be directing ortho to them. And so how do you decide who wins? Who wins is whoever's more strongly activating. And so these would be our next spots where we add something. You're definitely going to have a test question where you have one or multiple directing effects, and you have to circle where the next thing is added. And for that, be clear, I'm showing these colors to show them the work, but the answer we want would just be circling these. We don't want you to circle all 4 of them or anything. Yeah, you know the synthetic analysis advice. Carbon-carbon bonds, we can have Grignards attacking things, we can do Wittig, we can have a nitrile doing SN2, and we can have Friedel-Crafts. That's basically everything you know before Lecture 10. Lecture 10, whoa. A lot of carbon-carbon bonds. That's crazy. We're going to talk about it Friday. But that's most of what I have for you here for Lecture 9. And so the rest of our time is we're going to do some practice. Yeah.
Can I ask a question on like the directing?
Yeah,
For
please.
someone like the practice test, I'm kind of confused. We might do more practice with this later. When there are like 2 groups, one that's like withdrawing and one that's like directing. Like, how do we know? Do we go off of the stronger?
Sorry, one that's withdrawing, one that's directing.
I mean, one that's withdrawing, one that's activating.
Then you go with the one that's activating. Your winner is always whatever's more activating.
Always.
Mm-hmm. Cool. So what I have for y'all is I've made, 7 more box problems that are kind of exam level, close to exam level. Some I think a little bit harder, some a little bit easier. So I'm going to give y'all some time to work some of these box problems, and then we can do the final synthesis here together. Yeah, so in terms of timing, let's see. Why don't I give y'all like 10-ish minutes to try out some of these box problems, and then we will go over. Would you prefer to have more time to work and attempt more of them on your own, or would you prefer to talk about all the box problems together? Talking about them all. In that case, I might give you 5-ish minutes, and I want you to do 2 of the box problems. And ideally, don't do just the first two. Like, do any order. Try doing ones that look hard. Do ones where you're like, that scares me. And then we'll talk through all of them.
I'm sure
So I know I didn't give you much time, and now I'm going to go through these incredibly quickly, just to try to hit all of them so that we like say a few words on each. So osmium, it makes a glycol, so it makes the OHs added on both of the carbons here. Then we have alcohols, we have H+, and we have a ketone. We're doing the acetal reaction. Now when we do this, notably, did we make stereocenters? Yes, we made stereocenters, but is this compound chiral? No, it's meso. So you don't need a plus minus. So we have a base of our acetal, we have our bonds to O, and then we have this boy. And I can put them on wedges or I can put them on dashes, they're the same, but I'm just going to do this to show that they are the same. But we don't need a plus minus, we don't need any other stereochem. Next one, DCC is going to make an amide. So we do the version where we have this with our NET2. And then where we're doing reductions. Does the reduction affect the amide? Yeah, we can reduce the amides to amines. Does it affect the nitrile?
Yes.
Also, yes. So what we're doing, NET2 over here, and here, this is going to turn into a primary amine. So we have our carbon from our nitrile, our nitrogen from our nitrile, and they've been fully reduced. Also, for this one, we don't have a mixture of products for the stereochemistry because we didn't interact at any of those stereocenters. Yeah?
It's kind of a question from earlier, but could you react with itself here because you reacted?
No, it doesn't react with nitriles. It only reacts with amines. When DCC was present, it didn't have an amine on the molecule.
But as soon as we react it as an amine, doesn't it then react with itself?
How? There's no DCC then. Yeah.
Can the nitrile be reduced by just LiAlH4 and NADH4?
Only lithium hydride. Yeah. The only thing that can be reduced by sodium borohydride is a ketone or aldehyde. That's it. Cool. Then here we have an ester. And then we're going to a ketone. Ooh, that's weird. But hey, that ketone's on a ring. So the thing I'm thinking about is Friedel-Crafts. I'm thinking about Friedel-Crafts like acylation. And so for that, what I want is I want the acid chloride version of this. So I want this. Okay, so how do I get from ester to an acid chloride here? Well, I can do an ester hydrolysis. So I'm going to use NaOH and then H+. You could use H3O+ here, that would be fine. Then I need to take it from there to a carboxylic acid to a acid chloride. So I'm going to use Sockle. And then from there, I need to add benzene and AlCl3. And that will finish off the Friedel-Crafts. With question 4, we're in alkene land. So the thing I'm noticing about the top one versus the bottom two, the top one has an additional carbon. So what's a way of making an alkene that also adds a carbon? Vidig. Yes. Okay. So we need to add one carbon, right? So I'm going to write my single carbon Vidig, CH2, PPH3. Plus minus. And then we don't have a second step for that. So we're just good. We can just introduce the ylid. Then we have an internal alkene versus a terminal. And both of these, we know we're going to do via like E1 or E2. But is a ketone a leaving group? No. So let's first get out of oxidation level 2. Let's reduce it to an alcohol. So I'll do NaBH4MeOH in both of these cases. And then can I do an elimination directly from an alcohol? If I conk it. So if I conk it, H2SO4, we make this carbocation. Can that rearrange?
Yeah.
Yeah, it's next to a tertiary carbon, so that's going to make this carbocation. The hydride shifts over. But then we're still going to form the same alkene that we want, so that's fine. That one works. Over here, if we want to do this terminal one, we can't conk it. We have to do like E2 elimination. And specifically for terminal, we need our bulky base. So we need to use a Cotbu, Hotbu. But we can't do that on an alcohol. So we need the alcohol to be a better leaving group first. So I'm going to turn it into like a bromine. You could turn it into whatever leaving group you want. PBr3.
Can we make it into water?
You mean,
Like H2O, so it's a better. Like add the hydrogen so.
in which case, yeah.
Make it a better leaving group.
So that's the boiling in an acid strategy.
Yeah.
The issue is when you're boiling in an acid, it could do what you want and it could do SN2, or because it's secondary, it could do SN1. And then you would have a rearrangement and you would get a mixture of products. So it's just messier that way. Next one, chromium with pyridine, we oxidize to a ketone. Then we have an ylide here, so we're doing the Wittig reaction. So the way I do it, the most common mistake with a Wittig is adding or subtracting carbons. So I always count 1, 2, 3, 4, 5 carbons here. And then your 1 is the carbon in the alkene up top. 1, 2, 3, 4, 5. So we have this, and then we have the, is that the Simmons-Smith, I think, the one that makes the cyclopropane. So what we need to do is, we know that this makes the Z alkene right here, right? So we know that these long carbon boys need to be cis to each other. So the way I do it is I would draw the cyclopropane wing, and then on one of them I would put the ethyl on a wedge and the methyl on a dash. On the other one, I would put the 1, 2, 3, 4 carbons. 1, 2, 3, 4 here. Now with this, we could have also done this where these bigger port groups were added on the dashes, and so we have to do a plus minus here.
Was it the Wittig rule to have it in Z alkene or?
Yeah, the Wittig parfumology forms a Z. And to be so honest, we don't give y'all a reason why. Take more organic chemistry to find out. 6. Okay, I'm seeing a bunch of ethers. I'm seeing ether city. I have an alcohol and I have a ketone. Well, for me, personally, when I'm trying to make an ether, my first line of defense is the Williamson ether synthesis, which starts off with alcohols. So why don't I make this other one into an alcohol? NaBH4 MEOH. So now that's an OH. And then Williamson ether, I can do them to both at the same time. NaH deprotonates. And then I want an ethyl on the other side, so I do ethyl bromine. Last one, I make a Grignard. Then I attack my epoxide. Does it matter which side I attack here? No, because it's symmetric. So this is the 1, 2 of my epoxide, and this is my 1, 2, 3 of my starting material. Okay, then H plus workup, and then chromium with H2O, so it gets oxidized all the way to a carboxylic acid. So again with these, I honestly think that the hardest part of it is clocking what's going on and which reaction to use. And so the most powerful tool that you can use for that is your reaction webs to get everything together so that you can just think through them quickly. I know that that was probably an uncomfortable speed to go for us all to go together. But here we are. Any questions on this before we do the last synthesis together? while we only have one more section left, too. Oh, my class is coming to a close. Which I know that y'all are probably like, I'm ready for it to come to a close. Cool. Let's start off. Let's analyze some things. I see a benzene, and the benzene is probably a benzene here in the products. I'm seeing an alcohol, and I'm seeing an imine. Imine, we only know one reaction, so let's do our one imine reaction. Let's add H3O plus and hydrolyze it. I don't even know if that's the right move in terms of the problem, but it's the only reaction we can do. So we'll do that. Okay, boxy boy over here. This four-membered ring is probably this four-membered ring, which means this carbon at the base of the imine is this carbon. And then I'm going to guess that these three methyls here are the chicken foot in the product. So several things going on. We're putting things on a benzene, right? So our three things that we have are Blom, Blom, and Blom. If we are adding carbons to a benzene, it's either Friedel-Crafts alkylation or acylation. Chicken foot, is this alkylation or acylation? Did we add this just as an alkyl group, or did we add it as an acyl group and then reduce? Just an alkyl group. We could not have had an acyl group because that would be a carbon with not even 6 bonds. So we know that this was a Friedel-Crafts alkylation, which means that our electrophile was either this or it was this. Over here, if we have this OH in this position, does this seem like this likely came from just a Pelagian alkylation or an acylation? Acylation. So it probably started off its life as one of these boys that was added and then we reduced. Okay, and then we have our NO2. So anytime we're adding things on a benzene, we have to think about directing effects. So question, should I put on NO2 on the ring first? No, why?
It's so deactivated, you can't.
We couldn't do either of these Friedel-Crafts, totally. So my last step is going to be adding the NO2 probably. But then also, okay, let's imagine we're trying to add our NO2 and we have these two things. How does that tert-butyl direct? Orthopara or meta? Orthopara, it's activating. Great, so it directs there. But then how does this group over here direct? Well, the thing closest is just a carbon. It's kind of like an alkyl, so it's going to direct, there, orthopara to it. So we're going to get a mixture of things. That's not good. What if we consider the directing effects of when it was a carbonyl, though? So if we back up to this being a carbonyl here, now carbonyls are going to be what directors? Meta. So it's going to direct meta to it, which is ortho to our Friedel-Crafts alkylation. Do you see how here the directing effects of these two groups agree? So I think that our steps are going to be, we have it like this, we add the nitro group, and then we do that final reduction to an alcohol. Let me write it out. So what I'm saying was, it seems like we are going to be at this molecule. Then from here, we are going to, once we have the correct directing effects here, we are going to add our nitro group, HNO3, H2SO4. NO2. And then our last step is going to be NABH4 MEOH. I don't know how we got all here, but just looking at directing effects, looking at the things that we had to have added, we know that these are probably going to be our last steps. So now the question becomes, how do we get our Friedel-Crafts alkylation, acylation reagents? So maybe let's start off with the box. The box here needs to become an acid chloride or add an aldehyde. So it seems like we need to get into CAD land. What's our one-way ticket into CAD land? Chromium. Yeah, great. And technically it's not one way, because you can reduce out of it with lithium hydride, but okay, so then how do I make this into an acid chloride? Sockle. Great. Okay, then the other one, how do we make a fructose alkylation reagent? So we need to turn this into something that can do Friedel-Crafts. It's an alcohol right now. So do you think we want to do the chlorine route or the carbocation route? So there are a bunch of options, and most of them are correct. One option that you could do is you could do conc H2SO4 alkene, and then you could use like HCl, and bada bing, bada bang, you're there. One thing that you could not do, you could not go SOCl2 pyridine. Why can you not do SOCl2 pyridine to get this? Yeah, and this reaction requires an SN2 step. Another thing that you could do to get here is you could boil an acid. Not great, not a great strategy, but nothing else can really happen on this molecule. It's so small. It's not going to like rearrange or anything. So that's one that you could do. And then from here you could do this plus AlCl3 and benzene. And that's going to make this. But I'm going to say that there's an even cooler, not cooler, there's just a different way that you could do it. You could do H+. Or honestly, you would have to do a strong acid. So maybe I'll say like concentrated HBr, something like that. And you know that in this reaction, it makes the carbocation. And so if you have benzene around, benzene can just attack the carbocation. So that's one way to do it. I would say this blue route is safer. This route, I think, is more like big brain strat that like could get you in trouble on the test if you try to do it and you're not like exactly right. So cool. We have this. We need to get to this. Well, we're ready. Is this ortho-para directing? This terbutyl? Yeah, and do we want it to be added to the ortho or para position? The para, yeah. So all we have to do from here is combine in AlCl3. And we've synthesized. So, with all of this, please get sleep. If you go into the exam and you're too tired and you can't think, you won't do well. Y'all are gonna be fine. Y'all are gonna show up a little bit before 10. Make sure you get your seats and you're ready, and you're gonna have a little breakfast. Today, you're gonna be kind to yourself and others. You're gonna study. You're gonna encourage your friends in studying. And then we'll see you tomorrow for the exam. I'll stick around for any questions, but I'm rooting for you. You've got this. Bye.